So in this class, we are going to study what are the filters and why is SNR or signal to noise ratio is very important in a communication system. And what is the importance of filters and why we use these filters. So just look at this slide and let's see, and you see one signal. This is signal. And this is a low frequency signal, right? And you have a noise which is represented by a very high frequency signal. So a low frequency signal has a very high frequency noise. So V1 voltage is much greater than V2, right? However, when we see the this figure, we have a very high frequency signal, because now this is our signal, which is a high frequency signal, which is contaminated or ridden by a very low frequency noise. So the reason why we are actually dealing with this step. There are some times when we need to actually get rid of, for example, in this case, we are interested in our signal. We are not interested in the noise. So we want to get rid of the noise. What we want is that we want to pass this response to a filter which can actually filter out the low frequency noise or low frequency components of the signal and only pass the high frequency. However, in the previous one, what we are interested in, because the signal is a low frequency signal, so we want to retain our low frequency and get rid of the high frequency. So in this case, we need a low frequency signal and we want to stop all the high frequency noises. So this is why the filters are important. This is why the filters takes place, because sometimes in a communication system, we want to pass certain frequencies and block the other frequencies. So if you see this circuit, which is a first order filter circuit, it comprises of resistor, a voltage source Vs, a resistive element Vr, and a capacitor, right? So impedance of a capacitor is mentioned, which is 1 over j omega c. We studied how we calculated the impedance in our previous lecture. What is the voltage Vr across this resistor? The voltage, we can simply find this voltage using the voltage divider rule by R over R plus 1 by j omega c times, let's talk in phasor domain, Bs, or the complex domain. And what is the voltage across the capacitor? The voltage across the capacitor using the voltage divider rule is R plus 1 over j omega c times the source voltage. So let's say we have very low frequency, right? Which means that omega is very small quantity. If omega is very small, omega is nothing but 2 pi f. If omega is small and our capacitance V1 over j omega c is a frequency dependent component in this circuit. So this means that 1 over omega c, because this is the inverse, is much greater than R, right? If this is much greater than the resistor, and we in our this, let's name this as one equation, this is a second equation. If we want to find out the resistor voltage given the condition of low frequency, which means 1 over omega c is much greater than resistor, then we can ignore the resistor in the denominator and we can simply write as 1 over j omega c times Vs, which is nothing but j omega c R times Vs. And we can write the capacitor as 1 over, as we have mentioned in equation number 2, 1 over j omega c over R plus 1 over j omega c, and we can ignore this R because this is much small, and we can write simply, Vs as this voltage. So this is very interesting to evaluate, which actually show us that all the source voltage appears across the capacitor at low frequencies and virtually no signal appearing across the resistor. So which kind of filter is this? Is it a low pass filter or a high pass filter? Right? It is definitely a low pass filter, and that's how we have designed this filter for low frequencies. So this is a low pass filter. All right, so let's say we have very large omega frequency, which means that 1 over omega C for a capacitor is much smaller as compared to the resistor. So this means this is the high frequency circuit we are studying, right? So in that case, the voltage across the resistor, right now, what we are ignoring is we are ignoring 1 over j omega C from equation number 1, and we are writing R over R times Vs, which is equal to Vs. And voltage across the capacitor is going to be times Vs is equal to 1 over j omega Cr times Vs. So looking into this check mark, we can definitely see that the source voltage now is appearing across the resistor, and virtually there is no signal across the capacitor. This is why this is a high pass filter. Right? So this is how we can design the circuit to actually use for passing low frequencies or high frequencies. So now we need to find out what is the cutoff frequency, right? What is the cutoff frequency? If we consider R equals to 1 or omega C, we can calculate again the same voltage across the resistor by R over 1 plus j omega C times Vs, right? Since R equals 1 over omega C, so this is nothing but 1 over omega C over 1 over omega C plus 1 over j omega C. So I can also write this one as 1 over 1 plus 1 over j, right? This 1 over omega C cancel out because it's common for all. And 1 over omega, so again, I repeat, and I did that in previous lecture as well. 1 over j is nothing but 1 over j times j over j, which is j over j square, which is j square is minus 1, so it is minus j. So we can replace this by minus j times Vs. Sorry, Vs will come in every equation. What is this? How is this represented in phasor? Right? How can we represent this in phasor? Again, phasor is represented by its magnitude Vp and its angle phase. So it is 1 over, what is the magnitude? 1 square plus 1 square and under root, which is under root 2. How? And what is a theta? Right? What is a theta? How will calculate theta? So, okay, let me see. Vp is 1 square plus 1 square root 2. And theta for this one is equal to tan inverse y over x. And y is minus 1 over 1. So tan inverse negative 1 is equal to minus 45 degrees. So if this is minus 45 degrees here, this is 45 degrees minus 45 degree here. This is Vs. When this goes up, this is going to be 1 over under root 2 angle 45 degree times Vs. Right? This is just to solve this one. Right? I hope it's clear. So, and just to remind you that 1 minus j can be represented on this real and imaginary axis also as this is 1 and minus j is going to be on this vertical line on minus j line. So this is a plus j on top and this is minus j. So this is minus j. So 1 minus j is going to be somewhere here, right? And this is how this is going to be. This is minus j. And the angle is minus 45 degrees, right? And what is the magnitude for this one? It is under root 2. This is under root 2, right? Of this vector. Now, what is the voltage across the capacitor at this condition R equal 1 over j omega c? I'll use another color for clarity. Voltage across the capacitor is going to be 1 over j omega c plus R plus 1 over j omega c times Vs. So at R equals 1 over omega c condition, we can write this as minus j. 1 over j becomes equal to minus j. And we'll cancel out the others. So this is going to be 1 minus j times Vs. Again, how this is going to be represented in phasor. This is very important. So minus j, magnitude for minus j is nothing but 1, right? Magnitude of 1 minus j as shown exactly here, as shown here, because this is also 1 minus j, is under root 2. 1 square plus 1 square, root 2. Now angle, what is the angle for minus j? All right, so what is the theta for this one? What is the theta for this one? Times Vs. Minus j, the angle for minus j, where is this? How is this represented here? Where is minus j on this scale? This is the real, this is the imaginary. So minus j is here, right? So angle of minus j is minus 90 degrees, right? So this is one angle minus 90 degrees. What is the angle for 1 minus j? We already calculated. This was under root 2 minus 45 degrees. So this can be written as 1 over root 2 angle minus 90 plus 45 degrees times Vs, which is equal to 1 over under root 2 minus 45 degrees Vs. Right? So you can also so one thing I would like to show you is if you want to calculate minus j, what is the theta value of minus j? How will you do that? We know that theta is equal to tan inverse y over x. But in this case, the x is 0. So, right, so it should be tan inverse infinity then, because if tan inverse y over x is equal to theta, y is minus 1, but x is 0. There is no x component. So we are basically calculating tan inverse of infinity. What is tan inverse of infinity? Right? How will you find out tan inverse of infinity? You can find out tan inverse. You know that, I'll write it here. Tan of pi by 2 equals to infinity. So pi by 2 is actually tan inverse of infinity, which is 90 degrees. So that's exactly how we represented this here. And that's exactly what we wrote here, minus 90 degrees, right? That's a very important to understand how we are representing it in different domains, right? All right, so we can write this as cutoff frequency as omega c equals to 1 over RC. Omega c is cutoff frequency, which is equal to 1 over tau, which is equal to 2 pi fc. And what is fc is our cutoff frequency, right? So if you see this one, this figure is actually summarizing the two filters we just studied. At low frequencies, this is the low frequency behavior. At low frequency, this is at low frequencies. What is happening here? Right? At low frequencies, the voltage Vs, which is the source voltage, all the voltage appears across the capacitor, right? However, at high frequencies, the input voltage Vs appears across the resistor. And this middle point is actually your cutoff frequencies, right? So this is the frequency scale or the log scale on the x-axis, and this is the y scale, which is the voltage magnitude, right? All right. So what is a transfer function? Transfer function is nothing but output response with respect to the input response, right? And since we're talking in the complex domain, so we will write it as output over the input. Right? So whatever is the output, you can calculate with respect to the input, whether it's a low pass filter or high pass filter, right? So let's say it's a low pass filter, a first order low pass filter, in which the output is appearing across the capacitor. So what is the gain response on a log scale? So this here is basically on a log scale. This is the gain, right? So this part is the flat part, and this is the roll-off part. What is the roll-off part is? This area here is actually the pass band, which allows the frequencies to pass, which means that it is allowing the low frequencies until the cutoff frequency to pass through it. And then there's a stop band, which doesn't allow the frequencies to pass. What is the cutoff point? The cutoff point, FC, is the frequency at 3 dB point, right? So how we will write the frequency in, the gain in dBs. It is 20 log of base 10, the voltage, output voltage, with respect to input voltage in dB scale, right? And at the cutoff frequency, that gain is negative 3 dB. So at cutoff frequency, this gain drops by 3 dBs. Similarly, for a high pass filter, you have this high frequencies as a pass band, and the low frequencies are the stop band. And this is the cutoff frequency, and roll-off point is the negative 3 dB point. This is the gain. Gain is the output with respect to the input, right? So we will cover Phasor diagrams next time. We will also try to cover how you can solve basic AC circuit analysis using in the frequency domain now. So we have already studied different laws before, and we are going to study all of them in now complex domain. Thank you very much.